Thank you guys so much for coming tonight. And thank you so much, Rick, for being willing to give the talk. It's great to have you back again.
Thanks.
And all of your continued support is really, really appreciated.
Thanks.
So for those of you who haven't seen Rick before, he is a retired commercial pilot and also a former military fighter pilot. He's also an instructor and technical writer, and became an accomplished Christian apologist with a PhD in the history of ideas, which is where concepts meet culture. So please, give a warm welcome to our speaker for today.
Thanks, Joseph. Well, tonight is going to be a fun night, I hope. It's going to be fun for me. I don't know if it'll be fun for you. I find the whole thing about astronomy, the solar system, to be fascinating. And back when I was an undergraduate in the college days, I drew some conclusions that we're going to be talking about tonight that very few people think about for some reason. I'm just one of those weird guys who happen to think about it. And we'll talk about how orbits work. I went to the Air Force Academy. We take a bunch of engineering courses. One of them was orbital mechanics, which is just the math of how orbits work. The math is complex. The principles are not. The principles are really simple. And we're going to talk about those and show why some of the things you've been taught are simply wrong. So let's get started with looking at astronomy and how the solar system points to God, our Father. So this is from a series of videos, some teachings that we did at our church. It was called Human by Design. It's a series of 6 videos, and astronomy was number 5 of the series. The way different disciplines of science point to an intelligent designing creator. And so in this series, one of the things that I did was I used it as an opportunity to incorporate some history. My degree is history of ideas, which, as you mentioned, is where big ideas intercept culture and influence each other. So this was an opportunity for me to bring in this guy. This guy is my dad. And my dad was born in 1917. The reason I want to bring him in is because he has some relevance to how we validate history, how we determine that things are true. So this is him in about would have been about 1948 or so. He would have been 31 or 32. He got married in 1949, so it would have been in 1949, probably the only time he ever wore a tuxedo. He got married after World War II, but before World War II, on December 7th, which we're coming up on the 81st anniversary of Pearl Harbor. So Pearl Harbor happens. The next day, he and all of his generation pretty much go down and enlist in the Army. And within a year, he was in the uniform of our country and was involved with World War II from that point forward. He became an aircrew member on C-47s. And so I heard most of these stories growing up. Wasn't that interested, well, I was interested, but not as interested as I became later. Later in his life, he had a series of strokes and came to live with us. And this is him at about 19, when he was in his middle 80s, about 84, 85. And he came to live with us because some strokes had taken away much of his memory. But what he could remember was 50 years ago. He couldn't remember what he had for breakfast, but he knew what he did 50 years ago. And so he started telling me stories about World War II that I'd never heard before, especially after he had his stroke that put him at our house. And so I was spending time with him at the hospital. He was up in Nebraska. I was down here in Texas. I went up there to spend time with him. And the doctors told us that most of what you get back after a stroke happens in the first 2 weeks. And so you've really got to exercise the brain just like a muscle. And so I'm asking him questions, and the only thing he can remember is 50 years ago. So guess what I'm asking him about? 50 years ago. And so he's getting exhausted, and that does happen with stroke victims. And so he gets tired, and he says, well, why are you asking me all these questions? And I said, well, I'm just interested, and what I'm not telling you is your brain is going to die if I don't exercise it, so play with me here. Anyway, so he told me, well, why don't you just go look at my diary? Your diary? Excuse me? You have a diary? Yeah. Well, where's your diary? He said, it's in the desk at home. Where in the desk? Well, it's the top desk drawer at home. We'd never heard about this diary. And so guess what I did when I went home that night? Looked for the diary, right? So I was staying at his house. So this is the actual desk that was in our house all the time I was growing up, unsuspecting that there was anything of importance in it. So I go home, it's in our upstairs guest bedroom right now, and I opened up the drawer, and guess what I found? 2 spiral-bound notebooks. And these little spiral-bound notebooks obviously have become a family heirloom. Now, I believed what he had to say the first time, but knowing that there's written evidence, see, we're always looking for evidence, and knowing that there was some written evidence allowed me to go into this notebook and find some key things to validate the stories he was telling me. And so here is the entry from, if you look at the bottom down here, June 6, 1944, D-Day dropped paratroops without incident on Cherbourg. And there's a little more detail there. He was an aircrew member on C-47s where they dropped paratroops. And so the night before D-Day, they were involved in dropping troops that would be the first to land on the Normandy Peninsula. So when we find validating evidence, it confirms something that we thought might be true or weren't sure about. So we're going to look for some validating evidence about astronomy tonight, and we'll use that example of a notebook as we close up tonight. But let's move into astronomy. So here's what we're going to talk about. We're going to start with God's testimony, what God said about constellations, stars, planets, and moons. We'll move on to our place in the universe. Where are we really, and how do we define that? We'll look at the necessary conditions that make life and existence itself possible. And then we'll probably spend more time than anything else on this because it's really an important point, and I think it'll be new for most of you, how the solar system works and why it suggests design. So that's where we'll land. But let's look at what God says about what's God's testimony about astronomy and the stars. Psalm 8 is really good. It says, O Lord, our Lord, how majestic is your name in all the earth. You've set your glory above the heavens. When I consider the heavens, the work of your fingers, the moon and stars, which you've set in place, what is man that you're mindful of him, the Son of Man that you care for him? You've made him a little lower than the heavenly beings and crowned him with glory and honor. And it goes on, and it says, you made him ruler over the works of your hands. You put everything under his feet, all the flocks and herds, the beasts of the field, birds of the air, the fish of the sea, all that swim in the paths of the sea. A lot about the seas here. O Lord, our Lord, how majestic is your name in all the earth. So when we look at this passage, we see that there are a number of references to astronomical things that matter to us for tonight. So it talks about the heavens. It talks about that a couple of times. It talks about the moon and the stars. And it says, it asks these questions about what is man that you're mindful of him in spite of this incredible grandeur. So when we look at mentions of these things in Scripture, the sun is mentioned 61 times by my count. The moon 144 times. These are important markers. The stars 55 times. Psalm 147, for example, he determines the number of the stars. He gives to all of them their names. Anybody know how many stars there are? That's the right answer. Nobody knows how many stars there are. When I first started looking at astronomy and teaching, everything I know about astronomy and geology, I learned from teaching junior high earth science, other than what I learned back in school. But at that point, there were something like between 1 and 2 times 10 to the 22nd stars. 10 to the 22nd. That's a really big number. I can't comprehend it. The deeper they look into space, the more that number in the exponent gets bigger. So now it's someplace between 10 to the 23rd and 10 to the 24th. They really don't know. But as far as we can look, as far as it's capable, that we are capable of finding things, we find stars, planets, galaxies. It's immense. So anyway, planets, it doesn't mention any planets specifically, but the planets would look like stars, so they would describe them as such to the ancients. Constellations actually come up a fair amount. In Job, we have mentions of the Great Bear, Orion, the Pleiades, the Chambers of the South, which would be a constellation as well. In Job, we have the Crooked Serpent, Pleiades, Orion, and then Pleiades and Orion and Amos as well. So there's some possibility that even some of the passages in Revelation, I believe, probably are referring to constellations, where it talks about some symbols there as well. So we see God using stars, planets, and constellations as signposts. So we know that it's all over the Scripture. Let's look at some of the things on which life depends. One of them is light. Now, you've all seen this guy before. It's a funny little lamp, and he emits light. And then my question for you is, as you think about this funny little cartoon, what is light? Anybody got a good definition? Good answer. We don't know. We have some characteristics. We know that light has the properties of waves and particles, but we can't really quantify light exactly. We know that it travels typically at the speed of light, obviously. But what is the speed of light, and is it always the same? Well, when we get into relativity, we find out that there's some quirky things that light does. We'll leave that at that point. But light is really important. Another necessary condition for life is gravity. So here is, this was the moon landing, and you'll remember there was a famous experiment that Galileo did where he dropped 2 different size objects from the Leaning Tower of Pisa, and they landed at the same time. So on the moon, they demonstrated that same experiment, only using a feather and a hammer.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
So gravity is a weird thing because it acts on objects with an amount of acceleration that is not due to the mass. It's due to the mass of the object that's attracting the object, but not due to the mass of the object being attracted. So again, what is gravity? Another good answer from the audience. We don't know. We can describe its properties. We can quantify. We'll come back to that when we talk about Newton in a couple minutes. But we don't know really what gravity is. Here's another thing we don't know that life depends on. This is an atom. This is a carbon atom. It has 6 protons. It has 6 electrons and a number of neutrons. And these electrons, we think of them as orbiting in different quantum energy levels. And so when I was growing up, everything was written in that they were in orbital shells, that they were orbiting. Now it's more like probability they're someplace in that region, but we don't think about them as orbiting quite the same way as we did before, and we find these strange principles that if you observe something, it's not where you observed it. And so again, but the interesting thing here is the electrons and the protons and neutrons, they all have the same charge. So neutrons are neutral, protons are positive, electrons are negative. So why don't they just attract to each other? And if the electrons are in these quantum energy levels, but the protons are all positive, what holds them together? Because they should be repelling each other. And so we have the strong force that holds the protons together and the weak force that holds the electrons in their energy states. And we don't fully understand those either. We have some pretty good descriptions of different subatomic particles. We've got the quarks and the up and down quarks and the Higgs bosons and all those things. But it's all a little bit philosophical. So we don't know for sure. So let's keep going. So let's look at this one. This is thinking about fine-tuning of the parameters of the universe. So when we look at things, the way these forces are balanced together, in order for life to happen, they have to be balanced perfectly. And this short video will show you how that works.
From galaxies and stars, down to atoms and subatomic particles, the very structure of our universe is determined by these numbers. These are the fundamental constants and quantities of the universe. Scientists have come to the shocking realization that each of these numbers has been carefully dialed to an astonishingly precise value, a value that falls within an exceedingly narrow, life-permitting range. If any one of these numbers were altered by even a hair's breadth, no physical, interactive life of any kind could exist anywhere. There'd be no stars, no life, no planets, no chemistry. Consider gravity, for example. The force of gravity is determined by the gravitational constant. If this constant varied by just 1 in 10 to the 60th parts, none of us would exist. To understand how exceedingly narrow this life-permitting range is, imagine a dial divided into 10 to the 60th increments. To get a handle on how many tiny points on the dial this is, compare it to the number of cells in your body, or the number of seconds that have ticked by since time began. If the gravitational constant had been out of tune by just one of these infinitesimally small increments, the universe would either have expanded and thinned out so rapidly that no stars could form and life couldn't exist, or it would have collapsed back on itself with the same result: no stars, no planets, and no life. Or consider the expansion rate of the universe. This is driven by the cosmological constant. A change in its value by a mere 1 part in 10 to the 120th parts would cause the universe to expand too rapidly or too slowly. In either case, the universe would, again, be life-prohibiting. Or, another example of fine-tuning. If the mass and energy of the early universe were not evenly distributed to an incomprehensible precision of 1 part in 10 to the 10 to the 123rd, the universe would be hostile to life of any kind. The fact is, our universe permits physical, interactive life only because these, and many other numbers, have been independently and exquisitely balanced on a razor's edge. Wherever physicists look, they see examples of fine-tuning. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. If anyone claims not to be surprised by the special features that the universe has, he is hiding his head in the sand. These special features are surprising and unlikely. What is the best explanation for this astounding phenomenon? There are 3 live options. The fine-tuning of the universe is due to either physical necessity, chance, or design. Which of these options is the most plausible? According to this alternative, the universe must be life-permitting. The precise values of these constants and quantities could not be otherwise. But is this plausible? Is a life-prohibiting universe impossible? Far from it. It's not only possible, it's far more likely than a life-permitting universe. The constants and quantities are not determined by the laws of nature. There's no reason or evidence to suggest that fine-tuning is necessary. How about chance? Did we just get really lucky? No. The probabilities involved are so ridiculously remote as to put the fine-tuning well beyond the reach of chance. So, in an effort to keep this option alive, some have gone beyond empirical science and opted for a more speculative approach, known as the multiverse. They imagine a universe generator that cranks out such a vast number of universes that, odds are, life-permitting universes will eventually pop out. However, there's no scientific evidence for the existence of this multiverse. It cannot be detected, observed, measured, or proved. And the universe generator itself would require an enormous amount of fine-tuning. Furthermore, small patches of order are far more probable than big ones. So the most probable observable universe would be a small one, inhabited by a single, simple observer. But what we actually observe is the very thing that we should least expect: a vast, spectacularly complex, highly ordered universe, inhabited by billions of other observers. So even if the multiverse existed, which is a moot point, it wouldn't do anything to explain the fine-tuning. Given the implausibility of physical necessity or chance, the best explanation for why the universe is fine-tuned for life may very well be it was designed that way. A common-sense interpretation of the facts suggests that a super-intellect monkeyed with physics, and that there are no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question. There is for me powerful evidence that there is something going on behind it all. It seems as though somebody has fine-tuned nature's numbers to make the universe. The impression of design is overwhelming. The heavens declare the glory of God. The skies proclaim the work of his hands. Day after day they pour forth speech. Night after night they reveal knowledge.
So thanks to the Reasonable Faith folks for putting that together. We can quit now and be happy, right? But we'll go on a little bit. There's another couple of things we don't understand, and they're necessary for life as well. So let's look at this one. This is time. Anybody ever heard of time? Do you have enough time? What is time?
Don't have time to learn.
Yeah, don't have time, exactly. So we can describe the passage of events. We can measure the very orderly passage of events. We time events for the Olympics. But what is time fundamentally? We can't control it. We can't influence it. We live within it. The present is the dividing point between the past and the future. We can describe it in many ways, but what is it actually? And it turns out that time is not constant, because within black holes, which we won't go into detail tonight, but inside black holes, time is probably moving at a different rate if we were to measure it than we would see here, because time is proportional to the speed of light, and even light can't move inside black holes. So even in our present galaxy, we see a massive super black hole at the center of the galaxy, and we don't know what's happening with time inside there. But we do know time is influenced by gravity and some other forces, again, so we don't fully understand time. And we'll go to one last place that we don't understand, and it's a fundamental important thing, and that is, where are you right now? Do you know where you are? If someone were to ask you, where are you in the big cosmic space, how would you answer? And that's what this short video.
Thinking caps on because I want you to imagine this situation. One day an alien friend texts you and says he's coming to visit. Then he asks for directions to your house. Would you know how to answer? I mean, I'm sure you know the street, city, and country where you
And
live,
it goes on and on.
but
So,
could you go higher?
The vastness
Do you know
of
where the
space
Earth is in the
something
universe?
that,
Don't worry,
that should
I'll help
boggle
you
our
out.
minds.
Earth
It
is
certainly
the third planet orbiting
bugs
the
me,
stars
but
we
there you
call
go.
the Sun.
We're going to move on.
The Sun is one of
So
the
let's
billions
talk
of stars
next
that make up our
about
galaxy,
how we
the Milky
do
Way.
planetary formation.
It's a
And
spiral
I'm going to show
galaxy,
you
which
again two
means we
videos.
can
I rely on
distinguish
experts
two
because I'm
basic
not an expert in
areas.
astronomy.
The historic
But the
quarter,
first one's going to be
the
how
bulge
we
where the
describe
oldest stars live alongside a
the formation of
gigantic black
planets.
hole.
So that's kind of
And
where
the
we're
modern
going is how
part,
do
the
planets
disk,
form and how do our
filled
solar
with
system
lighter
form.
elements,
So how
the
do we
perfect
describe
place
this for
for new stars
adults?
to form.
And then we'll look at how we
This is
describe
our
it for
neighborhood.
kids, and we'll look at the difference. So here's the adult
Specifically,
version.
the sun lies on one of the spiral arms called the local arm or Orion arm, or maybe not. Astrophysicists are debating whether the Orion arm is just like the rest or a kind of bridge between the Sagittarius and Perseus arms. Trying to figure out the shape of your galaxy when you only have a side view certainly isn't easy. But let's continue. The Milky Way is one of the 3 largest galaxies in the local group, a club that also includes Andromeda, the Triangulum Galaxy, and a whole bunch of little galaxies called satellite galaxies which orbit them. If these guys are small villages, then we live in one of the major cities. And in a few million years, our city will be a metropolis because the Milky Way and Andromeda are eventually going to merge. But we're not done yet. The local group and many more galaxies lie inside the Virgo supercluster. Although recent research indicates that we're part of an even larger structure called the Laniakea supercluster. Superclusters are mass concentrations of galaxies, but all around us galaxies are organized in other, far bigger ways, forming filaments or walls and vast voids that are all part of one great cosmic web. In any case, what superclusters have in common is that they're gravitationally linked, which means they will merge at some point. In fact, the entire Laniakea supercluster is headed toward a place where there are lots of galaxies, called the Great Attractor, a deceptively mysterious name. By this point, you're probably thinking this is an endless task that we're always going to find we're inside an even larger structure, give it a name, and add another line to our cosmic address. Well, surprise, we won't. Once the galaxies are grouped in this web, the universe looks the same in every direction. On the largest scales, the cosmos has a uniform appearance, and matter looks evenly distributed. In other words, from this perspective, there's no way to statistically distinguish one part of the universe from another, so we can't assign it a physical address. In summary, our address is the Earth, Solar System, Orion Arm, Milky Way, Local Group, Virgo Supercluster, Laniakea Supercluster. Zip code? Well, never mind. The thing is that this property, the fact that at a large scale the universe looks the same everywhere, in other words, it's homogeneous and isotropic.
And it goes on and on. So the vastness of space is something that should boggle our minds. It certainly bugs me, but there you go. We're going to move on. So let's talk next about how we do planetary formation. And I'm going to show you, again, 2 videos. I rely on experts because I'm not an expert in astronomy. But the first one's going to be how we describe the formation of planets. So that's kind of where we're going, is how do planets form and how does our solar system form. So how do we describe this for adults? And then we'll look at how we describe it for kids, and we'll look at the difference. So here's the adult version.
We're flying through a computer model that represents astronomers' best ideas about the star formation process.
Reddish colors indicate thicker dust. The temperature, less than 400 degrees below 0 Fahrenheit.
Or less than 240 degrees below 0 Celsius.
That pinwheel ahead is a protostar, perhaps 10,000 years old. Protostars arise when a dense knot of dust, less than a light year across, collapses. But the details of the process are not well known.
In the formation, what data did they use?
Orbiting around
computer
our sun,
models.
we find asteroids,
And did you notice
comets,
all the
and
language
planets
about
with
this
their
may have
moons?
formed, but we
But
don't
how
really
did
know?
our solar system form?
Okay, so there's a lot of hedging that
Around
goes on, and it's all
4.5
theoretical.
billion years ago,
None of this
a
has been
cloud of
observed.
mostly hydrogen gas
It's
and
been
dust
postulated, it's been computer
started
modeled,
to collapse onto
but
itself.
you can do anything with a computer.
It spun faster and
so
faster, flattening
let's-
out to form
but
a
let's see
disk
what they
with a
say to
dense
kids.
center. This center got so hot it started making light, and our sun was born. Around our baby sun, there was still a spinning disk of gas and dust. Over time, it cooled and came together due to magnetism and gravity. Close to the sun, metals and rocks began to form, but it was still too hot for other materials to become solid. They remained as gases. Further from the sun, where it was cooler, water and other ices could form. They came together to make larger pieces, called planetesimals, which then joined to make large planets. These planets had enough gravity to capture the surrounding gas and became the gas giants, Jupiter and Saturn. Some scientists think Jupiter formed first and was pulled in towards the sun by the swirling material in the inner disk. When Saturn formed, it moved inwards too. The planets got closer and swept up the gas between them. They then began to journey outwards together. Jupiter's large size stopped rocky material clumping together. The asteroid belt is full of these rocky scraps of the solar system. It might also explain why Mars is smaller than expected. When Jupiter moved inwards, it fed on lots of material, so later Mars had less to form from. In the inner solar system, chunks of metal and rock slowly came together to create the rocky planets. Within 100 million years, early planets were orbiting the sun with lots of leftover material in between. The young sun had a phase of releasing strong winds. It blew the extra gas outwards, stopping the rocky planets and early gas giants from growing. The outwards moving gas was pulled in around the snowball cores of the ice giants Uranus and Neptune in the outer solar system. Many of the leftover ice balls flew out into the spherical Oort cloud. They occasionally got flung inwards, becoming comets, and collided with the rocky planets. Perhaps comets brought ices and gases back to these planets, providing material for their atmospheres, and also bringing water to the Earth. For the first billion years, many stray pieces of rock and ice would have been flying around, creating lots of collisions. The Earth's moon could be the result of a large object impacting the Earth. Similar impacts may have reversed Venus's spin and knocked Uranus onto its side. Some of the planetesimals still floating around were captured by the giant planets to form moons around them. Scientists are looking to distant stars with exoplanets to see how they form. Maybe then we'll know if we truly live on a unique planet in a very special solar system.
So what do you see as different in the way the language is in this kids' version? Also from an authoritative source, Royal Observatory at Greenwich, right? So, must be authoritative. So what do you notice difference in the language? What's that? Well, they don't have as much of the, this may have happened, we think, it's all, this happened. We know that this is the way, there is so much wrong with this video, I can't begin to go into it. We'll go into some of the things as we go along here, but we talk to the kids with much greater certainty than we talk to adults. And so kids are taught from early ages that these things must be this way, and again, we don't know. So let's go to a more reasonable case for the solar system and why I think it might have been intelligently designed instead of an accident. So we're going to look at these issues, how planetary formation happens. We're going to look at cosmic cookie dough and spinning tops, the obliquity problem. We'll look at orbital mechanics, which is how orbits work and what's wrong with the ideas about where the moon formed in our common parlance. We'll look at intelligent design and the idea of protection and habitable factors. So that's kind of where we're going next. So let's start with the idea of how planets formed by looking at the solar system itself. Now you've probably seen animations that look something like this. This is the solar system, obviously. This is the inner planets with the sun at the center, and then Mercury, Venus, Earth, and Mars, and then Pluto way far out. You'll notice that they're in similar but not exactly the same plane of motion. The Earth's plane of motion is called when we draw a line across the heavens, we call that the ecliptic. It's the plane of motion of the Earth, and it's where we measure everything else from because we live on the Earth. So it's a convenient way to do it. But all the planets are in slightly different tipped orbits. They're not exactly the same, but most of them are at least similar. So if we had an original form and they said that everything was in a dust cloud, let's say you were going to form a planet out of what's out there. Well, if you're going to make cookies, you start with a recipe. And you know what you want at the end before you start. And so if you're going to make chocolate chip cookies, this is original Toll House chocolate chip cookies. But if you're going to make a different kind of cookie, guess what? You need a different recipe. It's a different set of ingredients, slightly different order in which you do things. With the icing didn't exist on the other. So you have different recipes. What about planetary formation? Is there a different set of dust that you would be forming planets out of if you're going to have these planets accrete or form together out of the dust cloud? Do you have the same, or do you have a different set of batch? It would have to be different because the planets are different. But why would the dust cloud be differentiated? If you had a dust cloud that the whole solar system is forming out of, what would you expect the planets to look like? They would look like each other, but they really don't. So if we look at the 9 planets, what you would expect is similarity, but what you actually see is something that looks more like this. They are different in mass, in density, in geology, in the amount of atmosphere, in the makeup of the water content. One of the silly ideas is that comets, because they have a water component, are how we got our oceans. Well, what about all the other planets? Why don't they all have oceans too if there were that many? Do you have any idea how many comets it would take carrying water to make the oceans that we have? It's utter nonsense. So there's another theory. So if dust cloud can't work, what about this? What if the planets were formed individually, were wandering around, and then were captured by the sun? And the idea is the planets are so different they have to have been formed separately. They were wandering aimlessly in space and were captured by the sun, and then their orbits were eventually stabilized in the position we see them today. This is where we go into how do orbits work. And I'm going to take you to my hero, Johannes Kepler. Kepler came up with the laws of planetary motion. And so we're going to describe these briefly. Again, conceptually, we're not going to do the math, don't worry. But here's what it said. The orbit of each planet is an ellipse with the sun at one focus. The second law, the line joining the planet to the sun sweeps out equal areas in equal times. And the third law is that the square of the period of the planet is proportional to the cube of its mean distance from the sun. Everybody got that? Okay, never mind. What we're going to look at is a little simpler than that. We're going to look at, first of all orbits are what we call conic sections. Now this is a classic mathematical cone. Okay, so all the lines, if you go from one extreme to the other, they're straight lines through a single point, and they're all at the same angle. That's a cone. And every orbit is what's called a conic section. It's a section of a cone. So you either have a parabola where it only intersects perhaps the top one or the bottom one, or you have one that slices across, and that's called an ellipse. That's how we mathematically define an ellipse. But we can draw ellipses fairly easily by doing something like this. If you have 2 focal points, and let me show you what that means. So if this is a focal point here, and there's a focal point over here, these 2 foci define the ellipse. And so if you, on any point around this circle, the distance from here to each of the focal points added together is going to be the same. So over here, this is going to be a short distance, but it's going to be a longer distance to the other focus. And so what that means is that any point on that ellipse, all of the sum of that point measured to each focus added together is going to be the same. That's an ellipse. Okay, it's a fairly simple thing. If you have a loop of string and 2 thumbtacks, you can simulate this by drawing it and keeping the string taut. Okay, so that's all the first law says. So the second law is a little more complicated. It says the line joining the planet to the sun sweeps out equal areas in equal times. What that means is the farther away you are from the gravity source, the slower you move. And so when we look at an elliptical orbit, when you're close to the object, you're moving faster and covering more angular distance. When you're farther away, you're covering more distance from the object, but less angular distance. So here's a cool video that kind of shows that. Each of these 4 segments takes a different amount of time, but it's the same area. So each of those 4 areas, the different shades of pink, are the same area if you're to do the math. Now what's impressive about Kepler, and you can see on the close side it's going a little faster than it is on the far side. It's a little slower over here. What's impressive to me about Kepler is he did this without a calculator, no computer. He did it by observing and making measurements and then doing calculations on paper with a pencil, probably. Amazing stuff. Okay, so that's the second law. The third law sounds more complicated, but it's actually a lot more simple. And it's just the relationship between the distance and the speed of the object is proportional. And so here's how that works. So if we had a typical planet, and we'll call this a sun, and we'll have a little planet here called Earth. And if we put these in motion, it looks something like this. So the planet's going to be in an orbit, a relatively circular orbit, but there is no such thing as a purely circular orbit. They're all ellipses. So it's a very slightly not perfect circle, if you will. If we put a planet farther out, that planet is going to be going at a farther distance from the center of gravity, so it's going to go slower. That's all this is saying, and it's saying that the relationship between the period and the distance is a square to a cube. Again, mathematically, he figured this out. And the reason is, the closer you are to the gravity source, the faster you have to move so that your centrifugal force pushes you out and exactly balances the gravitational force. So the closer you are, the more the gravity, and the faster you have to go. That's all it's saying. But again, he figured this out in 1609. You know, just amazing. Okay, well, so Newton comes along and he refines these things a little bit with Newton's laws. Every body continues in its motion unless it's disturbed and moved. The change in the rate of momentum is proportional to the force impressed, and every action there's an equal and opposite reaction. And he went a little bit farther. And so I'm going to do something a little bit dangerous and show you how to play with orbits. Okay? So if you go to this QR code, you can pull out your phones, and you can do this now with me if you want, or you can do it later, kind of save this reference, and I'll bring it up later if you need it again. But it is a really cool gravity simulator, and it does a number of, that's where I got the previous video as well. I just discovered that one tonight. So here's what this looks like, and we're going to go to the web itself, the internet. Is scary stuff. Let's see if it works. It's always dangerous to have live internet during a presentation. But if you go here and you tap on the model, and we're going to look at, first of all, to show how orbits work, we'll look at this one down here, which is the Earth and a satellite. And we're going to show the gravity force, we're going to show the velocity, the path, and the grid. Actually, we'll make the gravity force go away. We don't need that one right now. So if we animate this, what's going to happen is this is going to be a satellite in low Earth orbit. And it's going to go in a what looks to us like a circle. Of course, we know it's really an ellipse, right? Okay? So let's play with how the orbits work. Now, we know that if we want to, let me reset this. If we wanted to get this into a different orbit, we could adjust the speed very slightly, and it would become, now it's an elliptical orbit. Slow over here, faster over here. And it'll stay in this orbit forever. Okay, it's very, very stable. Whether it's a low Earth orbit or an erratic or elliptical, they call it an eccentric orbit, it will stay in this orbit until something changes it. Okay, so keep that in mind, and we're going to come back to this later, but I just want you to kind of understand. So again, there's two kinds of orbits. This is an elliptical orbit, which slices the cone that way. A parabolic orbit would be more like this. So if we reset this and we put the satellite out here, we give it a bunch more speed, what's going to happen is it will go, if I have this set right, oh, that one hit the Earth. Oh, that's not good. We don't want that. So let's try again. It needs more speed, a whole lot more speed. And now it's going to go away. It'll be a parabola. So if we reset it so we can maybe see what actually happens, and it's actually hard to do because these parameters are pretty demanding. But you'll see it kind of, well, even that's too much. But if you play with it, you can find examples where it kind of bends the orbit and it just reaches exit velocity and never comes back. So it's either going to be that parabola shape or it's going to be the elliptical shape. That's all orbits do, every orbit. It's a little more complex when you get more than two bodies. A three-body orbital system is really complicated, and we won't go there. Okay? All right, so that's how orbits work in general. Again, we will come back to that, but let's move on with this. Okay? So again, if we want to change the orbit, again, it will stay in this orbit forever unless we do something to it. So when the space shuttle was going, what they would do is they would launch the space shuttle, stabilize it in a low Earth orbit with the, let's say, a 200 mile above the Earth orbit, but then they wanted to get it to a 400 mile above the Earth orbit. So they get up to 200 miles, they do a couple orbits while they're getting all the systems up online, and then they have to do an intercept with the space station, which is in a higher orbit. So to adjust the orbit, what we do is we give it a little extra speed by lighting the rocket engine for a precise amount of time to give it the precise amount of speed we need. And so we'll do that symbolically here by just adjusting this amount of velocity right there. So we're going to increase the velocity just slightly. Doesn't take much. And we'll see that now it's no longer in the same orbit. It's now in a more elliptical orbit. But if I want to stay in that second orbit, what did I say? This is going to stay the same forever. So if I want to stay in that higher orbit, what do I have to do? I have to give it a little more velocity at that bottom point so that it stays in a new circular orbit. But that's the orbit we're in right now. We want to increase that slightly, just a little bit, and then now we'll be in a new higher circular orbit, hopefully where we can rendezvous with the space station. Okay? That's called a Hohmann transfer, H-O-H-M-A-N. The guy who designed that is a brilliant guy who worked for NASA, and his name was Hohmann. So it's called a Hohmann transfer. If you go back to your dorm or back to your neighborhood and you tell your neighbors, yeah, we were talking about Hohmann transfer the other night, and they'll be very impressed. But anyway, that's what it's called. But again, it will stay in this new orbit forever unless there's enough atmospheric particles that slow it down a little bit. And eventually these low Earth orbits where the space station is and where the shuttle is and now the SpaceX and all those things, they will eventually come back down. All of our satellites, unless they're about 10,000 miles above the surface or so, they'll eventually decrease their speed and come back into the Earth's atmosphere. So this was a slide in case the others didn't work. We're going to go on from there and we'll move on to, given what we know now, let's think about where the moon came from. Okay? So we've talked about planetary formation and the fact that it doesn't make a lot of sense that the planets would have been formed from a dust cloud. It looked like they must have been formed uniquely, but then the orbits kind of tell us, well, their position had to be uniquely designed as well to be balanced and to be in the circular orbits, relatively circular orbits where they are. So what about the moon? Where did it come from? Well, here are some of the theories. One of them is the capture theory. It was caught by the Earth's gravity and eventually stabilized. But what do we know about that? Once the Earth influences the gravity, it takes other impulses of energy changing the speed of that thing, or it will not stay in orbit. And the moon has one of the most spherically perfect orbits in the known solar system, or in the known universe. So how did that speed get adjusted? We don't know. But how reasonable is this capture theory? again, if we look at this and just thinking about this, what we know about orbits now, you should be able to understand that there's no good explanation for it being captured, or for any of the planets to have been captured by the sun for that matter. So let's move on to a different idea. This one suggests that it's called fission, and it suggests that the Earth was spinning fast enough that part of its mass started spinning off from the surface and eventually, again, separated and went into a higher orbit. Does that make sense? If it's spinning fast enough to separate from the Earth, what's it going to do? It's going to go away from the Earth and then come back to this original point, which is a collision, right? So that's a problem. Well, we looked at the accretion theory, and so that's the idea that the dust clouds just formed in this way. Again, we're pretty close to the moon, so why would the moon be geologically similar but different if it's that close? That doesn't make a lot of sense. But this is the one that everybody gloms onto. It's called the impact theory. Okay, and here's a short video that describes how that works in theory. So I'll read it, it's a little small. 4.5 billion years ago, all this was happening. The young proto-Earth glowed at more than 3,000 degrees Fahrenheit. So there's an object the size of Mars that's going to impact the Earth. Watch out, folks, here it comes. All life as we know it, no more possibility. Okay. So after the collision, molten rock is sprayed into orbit. And you're going to notice a transition here in the animation. Oh, there it is. And all of a sudden we just have a stabilization and things are coming together. As the rock cooled, it formed a larger image. Now, if you go to the internet and look for lunar formation, this is what they're going to describe to you. Okay? But there's a problem with this. So if we'll move on. But let me go back to this. Sorry about that. Okay, so here's the moon. And if what I showed you earlier, so if I get too close, it explodes, so I can't get too close. That's bad. So, but if I'm close to the moon, to the Earth's surface, and I have a bunch of velocity, because something comes in and does a chip shot. Think about like you're golfing, and I'm not a golfer, but I understand if you don't do it right, you better get a bunch of grass that gets chipped up, right? So if it's a giant chip shot, here's what's going to happen. The moon's going to be flung away, and it's going to come back to the starting point. Remember, it always goes back to the starting point. So but that was too much. We needed more velocity. So we'll give it a little more velocity, so it doesn't do quite that much. But it started at the Earth's surface, so it's got to be fairly close. So if we animate that, guess what? It's going to do the same thing. As many times as we do this, we'll get the same result. The other option we could do is we could give it even more velocity, put it close to the Earth. Oops, sorry. I blew up the moon again. Can you believe it? So if I give it a whole bunch of velocity out here, what's going to happen? It's going to, it won't come back. It says return objects. Yeah, so that's not going to work. So the bottom line is this giant chip shot would return all the matter either into escape velocity, where it goes away, or it's going to come back to its starting point, and it will never form a separate object, because this chip shot material can move to the distance, theoretically, of the moon at present, but then what's going to give it the extra acceleration to get it stable in orbit? It can't work. And so it's a problem. And in fact, we now have academic papers that are saying that this idea, in fact, the flaws in the giant impact hypothesis of lunar origin, says this hypothesis is implausible in its present form because, one, it possesses a low intrinsic dynamical probability, and two, the collision would have melted and differentiated the Earth and causing geochemical signatures quite different from those actually observed, and three, the collision mechanics caused the moon to be derived mainly from the mantle of the impactor, which is the thing that's coming. So it's mainly going to have the geology of the thing that impacted and not the thing from which it was impacted and separated. A lot of problems. So even the academics, when you go to the academic journals, they'll tell you this is not the way it happened. But if you go to Wikipedia, guess what you're going to find? You're going to find that theory. And the same thing we see in the asteroid belt. Now, it used to be, they said, that the asteroid belt was the result of a collision, that there was another planet between between Mars and Jupiter, and that there was a collision, and this is all the debris that now is in the asteroid belt. But then they realized, well, if that's the case, then the moon chip shot theory is dead. So now we're going to say it's just leftover dust from the formation of the solar system. So you'll find those two main theories. But again, neither of those are really plausible. So there's another question, and that is, all of the planets are revolving around the sun, but they're also rotating on their axes, right? So if we look at the different axis rotations and the direction that they are in compared to the Earth's ecliptic, that plane of motion, the Earth is here, well, first of all, Mercury is 0.1 degrees, almost perfectly perpendicular to its orbit. So it's orbiting in a revolution like this, and it's orbiting almost perfectly vertically perpendicular to that orbit. But if you go to the Earth, what's our rotation, or what's our tilt? 23 degrees. You know that from Cancer of Capricorn and Cancer and all that. And if you go to Venus, it's backwards. It's minus 177 degrees. So it's like upside down. So if everything is forming from the same accretion, from the same dust cloud, again, you would expect similar physical forces to cause the rotation on the axis to be similar to the plane, or to the plane of all the other planets, but it's completely out. And again, when we look at all of the revolutions, they're just all over the place. And again, while we've got this one up, just look at the difference in the formation and the geology of these planets. And then you look at different moons of Jupiter. You've got Io, which is the most, let's see, I'm not sure. No, Titan is the most volcanically active body in the solar system. And you've got Europa, which is an ice-frozen water giant planet. It's almost as big as Mars, but it's covered with ice, liquid water frozen. Why does it have all the water and Titan has none? I mean, it's just, it looks like things were formed uniquely, however that happened. So how do they do all that? So let's bring Isaac Newton back in. What conclusions did Newton draw from all this? Well, he had a magnum opus, which was his claim to fame. It's the Principia Mathematica. It's his philosophy of natural, everything back then was philosophy of this or that, because it's the way they did science. And in this book, he has some amazing stuff, but you have to go all the way to the end. So you have to pass all of the math and the graphs and all the hard stuff, which we're going to do. And we're going to go to his conclusions. So we have to go all the way to the end of the book. And we find this passage, which is called the General Scholium, or in the way he wrote it, Scholium Generale, oh wait, it's Latin. That's a problem, right? But we have a translation. So what did he actually conclude from all this stuff? I can't read Latin, but here's the translation of the key parts. He says, bodies projected in our air suffer no resistance but from the air. Without the air, withdraw the air, and the resistance ceases. In other words, in a vacuum, there's no slowdown because of the atmosphere. In this void, a bit of fine down and a piece of solid gold descend with equal velocity. And here he's repeating what Galileo said, but to the extreme, not just different sized balls, but a feather and a piece of gold. So similar to what the Apollo guys did. The same thing must take place in the celestial spaces above the Earth's atmosphere. There is no air to resist their motions, so all bodies move with the greatest freedom. And planets and comets will constantly pursue their revolutions in orbits given in kind and position according to the laws above explained. In other words, just like we said, all the orbits will stay the same unless they are influenced by some force, some impulse to accelerate or decelerate their speed. That's all he's saying here. So you already knew this. But though these laws may indeed persevere in their orbits by the mere laws of gravity, which we talked about, which we don't understand, yet they could by no means have at first derived the regular position of their orbits from themselves from those laws. Let me repeat that. This is really important. Though they can persevere in these positions, they can keep going forever. But these laws don't describe how they could have started. They couldn't have derived those positions. And that was Newton's conclusion. And he goes on, just a couple things here. It is not to be conceived that mere mechanical causes could give birth to so many regular motions, since the comets range over all parts of the heavens in very eccentric orbits. He even recognized that the comets, though they're regular, they're much different than the other objects that we see like planets and moons. And then his conclusion, after talking a little bit about the gravity and how that works on orbits, this most beautiful system of sun, planets, and comets could only proceed from the counsel and dominion of an intelligent and powerful being. Why would we draw any different conclusion? Because too many of us are materialists. And we think that there are no forces outside the material force of the world. And yet, all those things we talked about that we didn't understand, from light to gravity to the fine-tuning, all those things defy a naturalistic explanation. And so it turns out that an intelligent and powerful being, outside the forces that are created, that we observe, that we measure, that we don't understand, that entity must exist. So we can understand that from science, but we can also understand it from Scripture. So let's close with a couple of passages that are helpful. God said there would be people like this, but they deliberately forget that long ago, by God's words, the heavens existed and the earth was formed out of water and by water. They deliberately forget. They choose, one version says they are willingly ignorant of these things. But given that that's the case, we still have this curiosity. And I love this verse in Ecclesiastes. I have seen the burden God has laid on men. He has made everything beautiful in its time. He has set eternity in the heavens, in the hearts of men, yet they cannot fathom what God has done from the beginning to the end. We have this intense curiosity about how this stuff was formed, the solar system, the planets, all this vast universe. We have curiosity, but we cannot fathom even the extent of it, let alone how it was formed. So I think that means two things. One, with science, we will never be able to explain, discover how these things happened. And even if God told us, we wouldn't be able to comprehend it. So we can't fathom it in any way you measure it. So even though there are some things we will never know, but we shouldn't be worried about that. It says the secret things belong to the Lord our God, but the things that are revealed belong to us and to our children forever. Why? That we may follow all the words of the law. So we don't know everything, but what we do know, we should follow. That's the lesson here. And then this verse out of 1 Peter, where he says, his divine power has granted to us all things that pertain to life and godliness through the knowledge of him. So by knowing God, we can know about these things. Him who called us to his own glory and excellence, who's granted to us his precious and very great promises. So he's given us many of these promises, even though we can't conceive of how they came to be. And then as we're therefore to make every effort to supplement our faith with virtue, and virtue with knowledge, knowledge with self-control, self-control with steadfastness, and steadfastness with godliness, godliness with brotherly affection with love. Because if these things are yours and abound, they keep you from being ineffective or unfruitful. And that's what we want. We don't want to waste our time or energy or God's time or energy. Whoever lacks these things is blind and short-sighted and has forgotten that he was cleansed from his old sins. And so there's a lesson to be learned here from the solar system, and that is that we can't conceive of it, but we can conceive that there is an entity that had to have formed it. So what's our responsibility? Well, our responsibility is also found in 1 Peter, but in your hearts set apart Christ as Lord. Always be prepared to answer everyone who asks you to give the reason for the hope you have. So have some answers ready. Be willing to say, we can't know that one, but here's some things I know. They're revealed clearly in Scripture. Do this with gentleness and respect, and keep your conscience clear so that when those others speak against you, your good behavior in Christ may be put them to shame of their slander. So let's close with this. What is happening at the outer limits? We talked about that whole cosmic space issue of what it looks like uniformly. We know now from what we can determine that everything is accelerating, that is moving away from us. But not only is it moving away, it's moving away faster all the time. So the speed at which things are receding increases. They're accelerating. So if gravity is the principal force in the universe, why would things be accelerating? Good answer again, we don't know. We don't have any way to explain it. We don't understand that. There's so many things we don't understand, but again, there are things we can understand, and all of them point to a creator. So that brings us back to our original question. Have we found a notebook in a desk drawer that points us to an answer? I think for me, the answer is fairly simple, and that is that the heavens declare the glory of God. And so we can worship him knowing that there's limits to what we can know, but we can know that. And so with that, let me invite any questions you may have, realizing that the only bad questions are the ones that are never asked. The QR code here is to my YouTube channel, which has a number of teachings on it, including the 6-part series, the Human by Design series, and some other things. We have a talk on there that I gave, one of the talks I gave here, I think Evidence from God, for God from Morality is on there. So thanks to Chris making that available. Appreciate that. So you're welcome to go there and check that out. So what questions have I raised? Have I raised any questions? Or just confusion? My job is to sow confusion and hopefully a little curiosity.
How would you respond to someone who's, a Bible-believing Christian and says, I absolutely believe we serve a God who's so big and so powerful that it's no problem for him to create the heavens and the earth in 6 24-hour days by a huge miracle?
I can't disagree with that. I mean, that is possible. There's some ambiguity in the data. There's a challenge that we have with explaining starlight, for example, distant starlight. That's a separate talk that we can go into another. It's on our another talk we gave. Jason and I just teamed up with 2 other guys and did a talk on the age of the universe, and that's up on that website, where we have 4 different perspectives. And the simple answer is we don't know exactly what God did. It's far beyond our ability to comprehend. I think it's as magnificent of God to have done it in billions of years as it would be for him to have done it in the blink of an eye. So I would never separate in fellowship from somebody who I disagree with. My position on this is simply agnostic. I don't know what God did leading up to the days that are described in the creation week. But whatever he did, by the time Adam came along, it was a stable universe. And certainly by the time you start having life, which is when the plants appear, at that point, things have to happen in succession, or the things that were done on one day are undone if it's millions of years later, for example, before the next set of life comes along, because they're so intertwined. Plants can't live without the animal kingdom and vice versa. So once you get the sequence of events started that are recorded in Genesis 1, it seems to me likely that things happened in a fairly orderly sequence of events. But before that, I think there is some ambiguity, and I don't know what God did, but I'm comfortable knowing that he did it. It's far more important that we believe that God created than exactly how or when.
Amen.
Yeah. Did I answer your question?
Yeah, absolutely.
Okay. What else? Yeah. You're the only one with a hand up at the moment.
I have a friend who has mentioned, kind of similar to that whole, if the further you zoom out, it's just kind of uniform universe in every direction. And then he says there's no bound where that ends. And that it's probabilistically impossible for us not to exist or something, or for observers to exist. So what would you say to an infinite universe hypothesis?
Well, first of all, I think infinity is by definition philosophically impossible. God is infinite. He created what must be a finite a finite universe in some measure, but the measures that we have extended so far, we don't have a tape measure big enough. Every time we look farther, there's more there. So it's bigger than we thought. We don't know if there are boundaries, or if in his infinite wisdom, God has made it so far out that we likely will never discover the edges of it. And so we just don't know. But we do know that the time-space continuum is expanding. And beyond that, and it's expanding in all directions. I mean, 3 dimensions, not just left and right. So we don't know exactly how big it is, but it's bigger than we can imagine. And so the Hubble telescope saw a great distance. Webb telescope is now looking in the darkest spots in the sky and finding that the points of light as it concentrates, and what they do is they take a series of photos and they overlay them to get more and more resolution. And the deeper you look, the more you're finding not just stars, but fully formed galaxies. And so many of the points of light that we see are fully formed galaxies. They're not just stars. And it boggles the mind. So I don't know if I answered your question, but I've forgotten the question. But the universe is really, really big, and we don't know how big it is. But I don't think it can be, again, the little I understand of philosophy, I don't think it can be infinite, but it's really, really bigger than we thought.
Thank you.
Yes?
How about, common argument is the Big Bang theory.
Mm-hmm.
How does the expansion of the universe that you've been talking about debunk that?
It doesn't really debunk it. It's just that the Big Bang seems to me to be incapable of describing the order that we see. We have never seen an explosion create order. And so a random, no matter how many years you give it, you're not going to see physical forces that necessitate the order we see in things like the solar system. They mentioned in one of the videos the Oort cloud. The Oort cloud is a proposed region outside the solar system that every once in a while we get comets that descend out of the Oort cloud. Again, given what we know about orbits, they don't just suddenly change their orbit and decide to dive into the solar system. So the idea of the Oort cloud, for example, is an explanation that says, why do we still have comets that look like they should have disintegrated years ago? Because every time a comet passes, when that tail is visible, it's matter that is being vaporized from the surface because it's water mixed with other iron and nickel compounds and many other elements. But it's actually exploding material off the surface. So you can imagine how many passes by the sun can it do if the universe is 4.5 billion years old for the Earth, 13 billion years for the universe. How many passes could that comet have made without being completely disintegrated or being attracted into one of the large planets? And we've seen, just in the last couple of years, there was a comet that impacted, I think it was Jupiter or Saturn. Do you remember, Jason, was it Jupiter? So we see these comets having a life cycle. So we propose these things like the Oort cloud. Nobody's observed it. There's no evidence for it. It's just they have to have something to generate where these comets coming from. And so they propose this mechanism. But it's again, we don't know.
So if there's any other, one more question, and then we can go ahead and wrap.
And I'll stay if you have other questions, but yeah.
So I guess if someone were to ask me what the purpose of the planetary bodies were, I'd probably say to show the glory and splendor of God. But for as someone who has studied it, do you see a purpose in planetary bodies that are not Earth? Because if you're an atheist or something, it kind of just looks like rocks.
Yeah, so I think I do see purpose in the larger planets like Jupiter and Saturn. They do, if you look at the solar system, we're kind of protected from space debris that's wandering through. So the large planets like Jupiter, Saturn, Uranus, and Neptune, they do have enough gravity to attract some of the debris that'd be floating around. And then the asteroid belt is also a protective area. And then our atmosphere is a protective thing because meteorites typically burn up in the atmosphere. So there's a lot of layers of defense that God put in place, I think, to protect life. And I think the entire universe from Scripture is here to demonstrate God's glory, but also to have a stage on which He could create beings like you who are dearly loved by God and loved enough that Christ died to pay for each of us so that we could have a relationship with Him. So I think the whole thing is a magnificent stage on which God could show His glory and create beings who are capable of choosing to love Him and responding to Him. Not all do, but that's His goal. So it's a huge stage, bigger than any we could build in Broadway, but I think that's what it's for.
That's beautiful.
Okay.
Yeah, so let's all give Rick
Thank you.
Thank you so much, Rick.
Thank you.